Okay, so today's first speaker is David P. Sanders, and he's going to be talking about interval methods for scientific computing in Julia. So let's welcome him.
Are we good? Good morning, everybody. So I'm very happy to be here. This is a great conference. So I'm going to talk about some interval methods, so methods using so-called interval arithmetic. And I put a pretty general abstract in the program, but I'm actually going to restrict attention to mainly constraint satisfaction problems and applications of those. So this is joint work with my colleague Luis Benet. So what are constraint satisfaction problems? It literally means find some set called the feasible set that satisfies a set of constraints. And what do I mean by constraints? Something like this. So some inequality or maybe equality. Which involves, in this case, two variables, x and y. So that's going to be some set in the plane, and I want to find all the points, x and y, for which this is satisfied. So why might I want to do that? Well, this comes up in, for example, constrained optimization problems, which is very important in all kinds of fields. And, for example, if you want to find roots, well, a root is just a solution of f of x equals 0, so that's a special kind of constraint. You can think of it like that. So basically, that's my application area, sort of optimization, root finding, and they have, as we'll see, other applications. So if we look at that equation, and we've taken some analytical geometry class, we can see what form that takes in the plane. It's going to be an ellipse or some piece of an ellipse. But how can a computer work that out, right? How can we actually even talk about what shape a set is in the computer, and how can we calculate it? So that will be the subject of my talk today. And yeah, okay. So I'm just going to cut to the end of the talk and show you how we can actually do that in Julia today. Like you can download it, as I speak, in this interval constraint programming package. So it's using interval arithmetic, which I'll describe in a minute, and it's we specify. So this package provides a domain specialized or domain specific language for specifying constraints as inequalities. And it is going to provide a solution to constraint satisfaction problems for some small number of variables in a guaranteed, rigorous way, mathematically rigorous way, assuming that the code works correctly. So what does that look like? So we're going to load the packages and literally just type C equals at constraint and then fill in this formula just like I had it in the maths. This is the same formula that I had. So currently I can't use 1 over 3, I have to type 0.333, but I mean that's easy to fix. And I'm going to specify a box in the plane, a rectangle where I want to solve the problem, and then I'm going to call this function called pave, and I feed in this object that this macro returns, I feed in the box, and I feed in some tolerance that is the box size. So let me just show you what the result is of doing that. It looks like this. And I want to actually hide this for the moment. So it's going to give me some output that looks like that. So that is the shape in the plane that satisfies this constraint. And you see that there are 3 different colors, hopefully. There's blue, which is this ellipse shape. There's white, and there's pink. The pink is on the boundary between the blue and the white. So what are we seeing here? We're seeing that anything in blue is guaranteed to be inside this set described by this inequality. Anything in white is guaranteed to be outside, and anything in pink is on the boundary, and it doesn't know whether it's inside or outside. And if we choose a smaller tolerance, then we can not remove completely, but hide. So if I reduce the size of the boxes, and I redraw the new thing, you can see that the pink got smaller, it's almost invisible, and so you can get better and better approximations to the set. So I'm getting what I'm getting are inner approximations. That means set that something that's guaranteed to be inside, and outer approximation is something that's guaranteed to contain the set. And so, as you saw before, if I now change the way I draw it, you can see what it's actually doing. What it's actually doing is creating this paving or tiling of the plane, just like in my poster that you may have seen, except that these are with boxes. And so it's filling up this space with boxes and proving that these boxes are inside and some other boxes are outside the set. And so I'll describe how exactly we do that calculation today. So first of all, before describing the calculation, let's just see what that looks like. So this is the algorithm running, So I'm not really going to concentrate on what it does right now, but it starts bisecting this. I start bisecting boxes. So the green box is the box I'm processing, and I'm just bisecting. And that means dividing it into two pieces. And then for each piece, I work. So for example, this box, the first thing it does is right, here's a box. It contracts it. It shrinks the box and leaves this white space where it used to be inside the... it's difficult to control. This box here, this green box, I'm going to shrink it, and it makes this white space. It has proved that this white space is outside the set. This set is this annulus, this ring, that I don't yet know, right? I'm trying to discover that shape by this algorithm. And this is what the algorithm does. It's contracting the box, and eventually it can start proving there, the purple box that just appeared has proved that is inside the set. Right, so it goes along doing that. I'm just going to jump along to a later point, and we see that it discovers the shape of this set bit by bit. So that's the algorithm. It's called a branch and contract algorithm. Branch because it's bisecting, and contract because it's contracting. So I'm going to show how that contractor works. Okay, so, but now what happens if I change, the shape of the set? Then I get something like this. So, I can just change, because I have this package, I can just change this exponent 2 to a 3 and add a sign. I just did that like randomly, and I get this weird set coming out, right? So I guess nobody would have been able to guess what shape the set was, but the software can do it. And so again, we're seeing that this is guaranteed to be inside this set, etc. Okay. So let's look at another application, root finding. So here I have two functions, x squared plus y squared equals 1 and x squared minus y equals 0. And so here I've drawn them. They're now equality constraints, so they're just curves in the plane. And I started off with this big green box, and then I applied this object that comes out of this at constraint. That object is called a separator, and it contracts the box down to here. So we've proved already that this is outside, so that anything outside this inner box, I've proved that does not contain the roots of this function. And then I'm going to just take a sub-piece of that box, this piece here, and I'm going to apply these contractors one by one. So here you can see that it contracted it according to the blue curve, and it sort of just fit exactly the piece of the blue curve that was inside the original box. And now I apply the red contractor, and it just fits the piece of the red curve that's inside the original, the new box. And I keep doing that recursively, and it collapses down eventually. It's quite slow, actually, to converges quite slowly to this point that's the root of this system, right? So basically, I had to bisect the original box in the plane. I had to bisect that once, and then the contractors did the rest. And so that's key in higher dimensions. That's why these contractors are interesting. So how does all this work? Well, it works with interval arithmetic, which is a way that enables me to calculate using sets. So the idea, what I wish for is, given a function f, a real valued function, a function from the reals to the reals, like f of x is x squared minus 2 or something, I want to be able to find bounds on the range of this function. Well, actually, I want to calculate the range of the function, but that is equivalent to an optimization problem, minimize and maximize the function, and we know that those are in general difficult. But instead of actually getting the exact bounds, I want to just get some bounds. I want to get what's called an enclosure. I want to get a set, or an interval that contains this range. So how do I do that? So we're going to work with closed intervals like x, which is a to b. Actually, I'm using a different notation in this talk, which is a dot b, just so we don't get confused with arrays. And so what I want to do is, given a function f, on this box, I want to evaluate the bounds of f, or the range on this box. So I could do that by sampling from the box and taking maximum and minimum, but that'll give me only a sort of approximation. It won't give me anything rigorous and guaranteed, right? So how do I get something rigorous? I'm going to be using floating point arithmetic, so it sounds impossible. But so let's look at the way we actually do that with this simple function x squared. So I want to, if I have an input interval 1 to 2, that's all the real numbers between 1 and 2, and I want to square that interval, what does that mean? So we're going to define it to mean that we're going to square all of the elements every value x in the interval 1 to 2, I'm going to square it. And so it's not too hard to see that that's going to give me the interval from 1 to 4, right? Basically because the function is monotone or increasing in this region. But what about if I have minus 1 to 2? Then you might think, okay, so how am I going to, right, so how do I actually calculate that? I would just actually be able to take the least value and square it, and the biggest value and square it, and that will give me the result. But that does not work for this case because 0 is inside this interval, and so 0 should be in the output. Actually, the output is 0 to 4. And so what I have to do, in general, is actually split my function into monotone pieces where it's either increasing or decreasing. For example, for x squared, I'll split it into the negative values and the positive values of x. And then it turns out that for x squared, this is the formula that you can use, that you can just put straight into Julia and say, to square, and I'm going to define an interval type, and then to square that interval type, I do this. And then it will know how to square your interval in a guaranteed way. So the caveat is that you have to do that by rounding down the lower endpoint and rounding up the upper endpoint in order to make it completely rigorous. And that rounding is very annoying and is actually the main technical obstacle to implementing this stuff. And we have various solutions implemented in the package. So the package is called IntervalArithmetic.jl. We've been working on it for 5 years. It's now pretty mature, very usable, very fast, and almost correct. So I just literally load that package and generate an interval by this dot notation that is defined in Julia, but actually does not have a predefined meaning. X equals 1 dot 2 is going to generate something which is of type interval, which is displayed like this. And then I can just square that, and I can square minus 1 to 2, and I get the correct answer. So I can do a similar thing for binary operations like plus. So plus is simple. You just add the two lower endpoints, the two upper endpoints, and that gives you the answer. Other functions like times are more complicated, and the trig functions like sine are very annoying to implement. I don't recommend it, but it's all done. So hopefully correctly. And it passes a very pretty comprehensive test suite. So there's an interval standard document, IEEE standard, that was released a few years ago. And there's an associated test suite that's pretty extensive, and we satisfy all of the tests for all of the functions that are currently implemented. Okay, so you can do basic operations, and you can use, because it's Julia, intersection and union symbols, and it's just beautiful. You get code that exactly copies your maths, right? As we all know. And you can, output the empty set when you have an empty interval, etc. So that's all done. And so what's the point of all of this? So if you now have a complicated function, what happens if you put an interval in? Well, that complicated function, Julia will sort of automatically split it up into sub-pieces that are simple functions like square and sine. And so what happens is you put in your interval, and the first function acts on it and gives you out an output interval that contains the range of that function. And then that gets put into the next function along, and that gives you an output interval, etc. And so after all of that, you get that the output of your whole function is a new interval that is guaranteed to contain the range of your function over your original input. That's called the fundamental theorem of interval arithmetic. That's from the 60s. Okay, that's it. So that's the whole point. So the point of interval arithmetic is that, basically, that you can bound a function over an input set. And that's going to be really useful. For example, if I want to find roots of a function, I can find a piece of my space where my function, when I evaluate it with interval arithmetic, does not contain 0, and then that proves that the function has no root in that region of space. So I'm not really talking much about roots today. I've given previous talks in JuliaCon. You can go check that out, and there's some docs and stuff. Okay, what about in higher dimensions? I want to talk about sets in higher dimensions. So that answers my question. How am I going to actually even represent a set? As we saw, it's a union, a collection of tiles, and the tiles are rectangular boxes. And so they're basically Cartesian products of intervals. So x Cartesian product y is just the set of pairs x and y, where little x is in my set x, my interval x, and little y is in my interval y. That'll give me a rectangle in the plane. And so I can actually write that in Julia using this cross symbol that in base Julia means cross product, which is a total waste of this symbol. So I'm just going to reuse it to mean Cartesian product because I can talk about sets, right? So it makes sense to talk about Cartesian product of sets. And of course, I can create boxes in other ways, like here's a 5-dimensional box where I repeat 1 to 2, thanks, each time in 5 dimensions, etc. Right? So we can all of this is implemented in the package interval arithmetic. That's the basic package that all the other packages depend on. So we have packages for root finding, for optimization, for eigenvalues, and increasing number of interesting and useful packages that you can use from Julia in a very easy way. Okay, so we started. So now let's explain the magic, right? There's magic going on in interval constraint programming, which is that I write down this constraint and somehow I get an algorithm out of it. So I'm declaring a constraint in a declarative way, and that's why it's called interval constraint programming. I just sort of write down a constraint and it magically does something. And I want to convert that into an executable algorithm that can actually tell me what I need to do to solve that. And so one possible solution to that, a very useful one, is the forward-backward contractor, also called HC4, or HC4 revised, developed around 1999 by Bonnamu, and I think it's been rediscovered several times. And it takes a box, as we saw, it takes a box as input and contracts it to a possibly smaller box in such a way that any part of the box that got eliminated is guaranteed to be outside the constraint set. How on earth does it do that? That's the question. So let's just recall what that looks like. So here's the constraint set that I'm interested in and I'm trying to find, and here are some boxes that intersect that constraint set. So if I have a box that's outside, when I contract it, it'll just disappear. Maybe I should have drawn that. But if I have boxes that overlap, when I do the contraction, they'll do that, right? So I take the box, and it actually, this is an operation that's implemented, right, that's doing this. I'm putting in a box, and it gives me out a box that has eliminated stuff that lies outside this set. It still contains some things that are outside the set because it's a box and my thing is curved, right? But it's eliminated, whatever it eliminates, I'm guaranteed is outside the set. So that's what it does, and the question is how. So how does this forward-backward contractor work? I'm going to use my favorite example, x squared plus y squared less than or equal to 1. And we're going to draw the syntax tree of that expression using this package I wrote called treeview. So you just load the package and do add tree, and it draws the tree of the syntax tree as a tree. And so what we're going to do is, at each node of this tree, we're going to introduce a new variable, an intermediate variable, a, b, and c. And we're going to do stuff with those variables. What are we going to do? So what we're going to do is we're going to do a forward pass. It's called a forward-backward contractor. The forward pass does add these intermediate variables and then goes through and calculates the values of all those variables, basically evaluating the expression in the usual way. Then we impose the constraints that we're interested in at the top of the tree, and then we propagate that constraint information back down the tree in the backwards pass. So let's go through that actually as an example in Julia. So I'm going to start off with the entire plane. So I can use this infinity symbol, which is just an alias for the floating point inf. And so this is an interval that goes from minus infinity to infinity, the whole real line. I have x and y both being those, and so the Cartesian product of them is the whole plane. So I'm going to do a calculation on the whole plane all at once, the whole set, in a rigorous way. So I'm going to introduce these intermediate variables, a equals x squared and b equals y squared, as I said. And so x is this whole real line, and when I square that, I get just the positive numbers, right? The interval from 0 to infinity. So you can argue about whether infinity is contained in this set. I am not interested in having that argument right now. So c equals a plus b. That's at the top of the tree. When I add 0 to infinity to itself as intervals, I get 0 to infinity back. And now I'm going to impose the constraint. I'm going to restrict the allowed values of c. c is x squared plus y squared. That's what I wanted to constrain. I want to constrain that such that it's less than or equal to 1. How do I do that? I take the current values of c. The current values of c came from the original values of x and y. And now I'm saying I'm only interested in those values of c that are less than 1. So I'm actually going to intersect. So it has to satisfy an AND condition, right? It comes from the original thing, and it satisfies this constraint. And so that's done in set theory by intersection. So I'm taking the intersection of these two sets in Julia. Right? This is all executable Julia code, of course, that I ran beforehand because whenever I run it live, it always breaks. And then I'm going to take this constraint. So I have this new value of c, right? I modified the value of c. So now I'm going to propagate that back down the tree. So c was defined to be a plus b. A was one of these intermediate variables, so a is equal to c minus b. And so here are the values of those two things. So c minus b is now using the new value of c that was constrained. So a is the values coming up from below, from the roots, from the original values of x and y, as c minus b now has this constraint information encoded. And so, again, I need to do an and so I need to do an intersection. And so I'm going to propagate the constraint information down the tree by saying a equals a intersect c minus b. And that gives me this interval 0 to 1. And then I have to do the same thing again, and now I have the value of a, and a was defined to be x squared, so x is basically the square root of a. But actually it could be the plus square root, or the positive square root, or the negative square root. And so I'm going to do x equals the original value of x intersect the square root of a union minus the square root of a. So, this is exactly what you would write by hand, and it's exactly what you can write in Julia. And it gives the interval minus 1 to 1. And then you can do the same for y, and it's going to also give you minus 1 to 1. Okay, so what have I done? So I've done this series of like 10 operations with intervals, with sets, imposing this constraint, and I get out this box minus 1 to 1 times minus 1 to 1. So I get a square that exactly contains this disk that I'm looking for. So I did this contractor that takes the whole box and contracts it, the whole plane, and contracts it down to this box that I'm interested in. And I'm guaranteed, because this is interval arithmetic and I get overestimates, I get enclosures of sets, I'm guaranteed that this has not thrown away any information, any part of the set, of the constraint set that I'm interested in. It's pretty amazing. Right, so that's how these contractors actually work. And so what is the magic inside the package is this macro. So I talked about macros in my workshop briefly the other day. So we're doing metaprogramming that, as we all know from Stephen Johnson's talk yesterday, is a bad idea, but that's what we're going to do. Because in this case, it's a very good idea. So because we want to convert this sort of domain-specific language into an algorithm, into code. So so just showing that C exactly gives me this minus 1 to 1 times minus 1 to 1 that I just got out. And it gives me something else as well. And so what is this actually doing? It's creating an object called a separator. That separator contains a contractor that exactly does this forward-backward thing. And so here's the forward part. Here's the code for that. And it exactly has generated automatically, using metaprogramming, exactly the code that I just did by hand, right? A equals x squared, b equals y squared, c equals a plus b. This is automatically generated. That's the forward pass. It returns the output c and all of the intermediate variables in a list, in a tuple. Now I'm going to do the backward pass, and that's going to do these intersection operations that I did coming back, the propagation. And that uses these weird functions plus rev, etc., which are reverse or inverse functions. So these are actually literally calculating the inverse of, I had c equals a plus b. I need to invert that. I need to literally calculate the inverse function of that plus. And that's what these functions do. And this is all automatically generated again. And so it puts these in a contractor object, and that contractor object is a callable function. And when I call it on an interval, it contracts the interval using this algorithm. So these reverse functions are all defined in the IntervalConstraintProgramming.jl package, which, as I said, literally calculate inverse images or pre-images or inverse functions or whatever you want to call them, f inverse of a set. For example, the sine rev c, a function, you pass in two intervals, and that corresponds to, in your mind, to the formula c equals sine a. And so we're contracting it to mean that, okay, what we're going to do is calculate the intersection of c, the input, with the inverse of the sine function applied to a. So in other words, it's the set of all x in c such that the sine of x is in a. So all of these things are implemented. Again, they satisfy all the tests that we've implemented so far. And similarly, plus rev is more complicated because it's a function that takes two arguments, but basically it's, the inverse image is the set of all pairs that are satisfying that they add up to something inside this thing C. So it's a bit difficult to get your head around, but once you do understand what's going on, you see that this is a super powerful tool. And so, as I said, separators, well, maybe I didn't say it. So separators have actually kind of two contractors inside, one for the inside of the constraint set and one for the outside, because now we don't just want to contract, we want to prove what's in the inside and what's outside the thing. And so, okay, so we can do the maths, and then let's actually just look at what it looks like. So here's a box. I want to know which part of the box. So, originally what people did, which I haven't shown, is you just start bisecting this box. And when you find a piece of the box that you know is inside, because you just evaluate that piece with interval arithmetic, you show it's inside, or you show it's outside. But that's actually very inefficient. And so the contractor just makes the whole operation much more efficient. And so I'm going to take this box and I'm going to contract it on the inside and contract it on the outside, and I get this picture. So this piece here on the right is what the inner contractor removed. And this piece here on the left is what the outer contractor removed. So the contractor that was dealing with the outside of the box, right? So it took this original box and reduced it to this right-hand piece. And so there's this intersection of the two pieces, which is some kind of boundary box. And then I do a set difference of the whole box with these two pieces, and that gives me what was guaranteed to be inside and what's guaranteed to be outside. The set difference function is currently pretty inefficient. If anybody would like to help me, make it more efficient in the hackathon, that would be very welcome. Because that's, I think, a pretty big part of the time that it takes to run these calculations. Okay, and then we can do cool things like if we have two of these sets defined by two constraint sets, right? So a constraint satisfaction problem usually has lots of constraints. So here lots equals 2. I have two constraints, and I want to take the intersection and the union of them and see what that looks like. And so here's the answer, that these are two, there's a ring and an ellipse ring, and I'm taking the union in green and paving that, and I'm taking the intersection in yellow and paving that. And so you can see that we can calculate these things, and it's not taking a paving of one and a paving of the other and then intersecting them. It's just literally paving the intersection set. Okay, how much time do I have?
3 minutes.
Okay, so all of the code, because it's Julia, works in n dimensions. Of course, it's a pretty bad idea to bisect in n dimensions, and that's why we use contractors. So here's, I want to show an example in 3 dimensions. This is using Maki, Simon Danish's amazing 3D visualization package. What's not quite so amazing yet is the transparency. So it's a bit difficult to understand what's going on, but you can see that these are two solid tori, right? So I'm defining these tori using this add constraint. I'm giving the formula for a solid torus in 3 dimensions. The package works out that there are 3 variables, and and, well, it's actually down here. Yeah, anyway, it's the same. So, actually, I'm not sure it's a solid torus or if it has a hole in the middle or something. And the point is there's like 100,000 boxes in each of these things, and I just rotate it around as if nothing because it's OpenGL and because Simon has done some amazing magic to get this all working from Julia. And so these are supposed to be overlapping tori, and then I can calculate, for example, their intersection. And I can do that in principle in n dimensions. Okay, so we've already seen that this can be applied. So I'm not showing any particularly advanced applications. I wanted to focus on exactly how this all works. But basically, you can now just go ahead and take this. All we're doing now is taking this and incorporating it into your root finding software and your optimization software. So, for example, unconstrained optimization, that just means take a function f over a domain and find the minimum point, right? The point x where the function takes its minimum value over the whole domain. So we're talking about functions that are nonlinear, non-convex, right? So this is a huge, optimization is of course a huge world, but we're trying to get the global minimum and guarantee that it is the global minimum. And so how do we apply these methods? Well, given a box X, if we have a current upper bound of the global minimum, which is called M, then we're only interested in the piece of the box X which actually lies below the global minimum, because any piece that's above the global minimum cannot contain the global minimum, which is what we're looking for. And so that's exactly an opportunity to apply all of this technology of contractors. We're just going to contract. If we have a contractor, then we're going to feed in this interval minus infinity to m. That's the piece I'm interested in of the box. And we feed in the box, and it will return the contracted box that may be smaller. And if it's smaller, that means that I've actually proved that I can eliminate a piece of my x, and that will make my algorithm to find the global minimum much more efficient. So as I showed last year, we can actually do this in 500 dimensions in certain cases for nonlinear, non-convex functions using this technology. And in constraint optimization, it's a combination of two difficult problems, optimization and constraint satisfaction. And the difficulty is actually finding feasible points in an efficient way. And so these separators and things should be useful for that, but it's actually difficult to work out how to get that all implemented. So this is still work in progress. If you're interested in joining in, please feel free to come and find me at the hackathon. So that's the end. So yeah, in summary, I don't have a summary apparently. So I did have a summary. Seems to have disappeared. Sorry. So we have this GitHub organization, Julia intervals with all the packages, mainly in collaboration with my colleague Luis Bennett. And it's being applied in various other packages. And so in summary, we have these very powerful tools to calculate with sets in a guaranteed way. And we have these really nice contractors. And so if you have applications for those, please let me know. And here's my contact details. So thanks for your attention.
Thank you, David. Does anyone have any questions?
It's kind of a little bit obscure question, but I'm just curious, what's about integer domains? Like, is that kind of something that is just a little bit too silly to even consider?
No, that's a great question. I mean, you know, a lot of real-world optimization problems have integers, have booleans, all kinds of things. So I personally have not worked on that at all. I believe that there's various of these packages in Julia that deal with optimization. In particular, there's one called Alpine.jl. It uses some interval technology and uses some other things. And I believe that they do handle integer-valued variables. And it's a different world. I mean, it's much more complicated in a way. It's even more complicated. And basically, as far as I understand, you sort of end up doing a sort of, if you have, I really can't say much about it. But so there are all these acronyms in this optimization world. So that would be like MINLP, which is mixed integer nonlinear programming. So it's a mixture of at least nonlinear stuff, but you have some integer variables, and it makes it even harder. That's a great question.
If you define the interval as like 1 to 2 versus 1 point to 2 point, does that actually make a difference? Or
no. So in the current package, we don't allow integer intervals or rational intervals, just because the main point of the package is to deal with the floating point issues that arise, basically the rounding. It's very easy to code your own package to do intervals with exact endpoints. So it's like an hour's work, half an hour to just implement the basic functions. You can just copy the functions from our package, where we decided at some point that it wasn't worth supporting that possibility. So if you type 1.2 or you type interval of 1,2, that literally, so I can do show full of aunts, that will show you that actually I have an interval with floating point endpoints. Sorry. And that is of type interval parameterized by float64. I can do things like big of 1 to 2. I can solve root finding problems with big floats, so you can get arbitrary precision. So for example, I want to find the roots of the function x goes to x squared minus 2 over the infinite real line using big floats. And hopefully that will just work. Takes a while because it's compiling, or maybe it won't work. You should never do these live demos. Okay, it's not working. Let me not do that. Let me do that from minus 100 to 100. Okay, there we go. So we get a list of all the roots in that interval, And it guarantees that in those intervals, so you can see square root of 2 and square root of minus, and minus the square root of 2, it guarantees that those are unique roots using an interval version of the Newton method and that kind of thing. So yeah, basically all of these packages just work with floating point endpoints, but you can use big floats. So there's the one where, so I'm proving that there are exactly 2 roots of this function over the whole real line in sort of 1 second.
256 is the default precision.
That's the default precision, yeah, I can
But
adjust.
can you adjust that?
Yeah. I forget how to do that. I think it's set precision interval 10,000, and then, roots equals this, and then roots 1, sort of show full of that. No. Okay, at format full roots 1, there are that's the precision, and then I do diameter of that thing, interval, and it will tell me that it's 10 to the minus 32 width. So I proved that the root lies within an interval of width 10 to the minus 32. So that's because when I ran the code, there's a default tolerance, so I can just change the tolerance to 1 e minus 1000, and I don't remember how to use this package, apparently. So I don't know what's going on. Yeah, that's strange. It should just work. Okay, don't remember, but you can change the tolerance, and I don't remember the syntax. Sorry. Yeah. Whatever. Yeah, you can do it, and you can get these super precise roots. And it's very quick, even though it's using big floats, because the Newton method is very quick. In higher dimensions, it's not so quick. I mean, higher dimensions is difficult, right? So, sorry, I should stop. Thanks.
So let's thank David again.
Thanks a lot.